Mastering cloud-native architecture. Ditch the servers, unleash the power. Which operational practices and design principles would you employ to ensure the successful implementation of serverless computing in a cloud-native architecture, where the focus is on achieving operational excellence, and how would these practices enable the development of scalable, reliable, and efficient systems that can efficiently handle variable workloads? To ensure the successful implementation of serverless computing in a cloud-native architecture and achieve operational excellence, several operational practices and design principles must be employed. These practices and principles are centered around the themes of monitoring and observability, automation and infrastructure as code, continuous integration and delivery, and management of technical debt. Firstly, to ensure operational excellence, it is essential to have a comprehensive monitoring and observability strategy in place. This involves implementing a monitoring system that provides real-time visibility into the performance and health of the serverless application. This can be achieved through the use of cloud-native monitoring tools such as AWS X-Ray, Google Cloud's CloudTrace, or Azure's Application Insights. These tools provide detailed traces of requests as they flow through the system, allowing developers to identify performance bottlenecks and troubleshoot issues. In addition to monitoring, observability is also critical to ensure that the system is operating as expected. Observability involves collecting and analyzing metrics, logs, and traces to gain insights into the system's behavior. This can be achieved through the use of tools such as Prometheus, Grafana, and New Relic. Another key operational practice is automation and infrastructure as code. This involves defining infrastructure and application configuration in code, such as AWS CloudFormation, Azure Resource Manager, or Google Cloud's Cloud Deployment Manager. This approach enables version control, repeatability, and reproducibility of infrastructure deployments, reducing the risk of human error and increasing efficiency. Continuous integration and delivery, C/CD, pipelines are also essential to ensure operational excellence. These pipelines automate the build, test, and deployment of code changes, ensuring that changes are thoroughly tested and validated before being deployed to production. This approach enables faster time to market, reduced risk, and higher quality. To ensure that the system is scalable, reliable, and efficient, several design principles must be employed. Firstly, the system must be designed to scale horizontally, using cloud-native services such as AWS Lambda, Azure Functions, or Google Cloud Functions. These services automatically scale to handle changes in workload, without the need for manual intervention. Secondly, the system must be designed to be loosely coupled and highly available. This can be achieved through the use of design patterns such as event-driven architecture, where services communicate with each other through events, rather than through direct calls. This approach enables services to operate independently, reducing the risk of cascading failures. Thirdly, the system must be designed to be efficient and cost-effective. This can be achieved through the use of cloud-native services that provide automatic scaling, such as AWS DynamoDB, Azure Cosmos DB, or Google Cloud Bigtable. These services automatically scale to handle changes in workload, reducing the risk of over-provisioning or under-provisioning resources. Finally, to ensure operational excellence, it is essential to manage technical debt effectively. This involves prioritizing and addressing technical debt through regular refactorings and improvements, ensuring that the system remains maintainable, scalable, and efficient. In terms of how these practices enable the development of scalable, reliable, and efficient systems, the following benefits can be realized. Faster time to market, automation and infrastructure as code, combined with C/CD pipelines, enable faster deployment of new features and services, reducing the time to market. Improved reliability, loosely coupled and highly available design, combined with automated testing and validation, reduce the risk of failures and improve overall system reliability. Increased efficiency, cloud-native services that provide automatic scaling, combined with efficient design principles, reduce the risk of over-provisioning or under-provisioning resources, resulting in cost savings and improved efficiency. Improved scalability, Scalable design principles, combined with cloud-native services that provide automatic scaling, enable the system to handle changes in workload without manual intervention. In conclusion, to ensure the successful implementation of serverless computing in a cloud-native architecture and achieve operational excellence, several operational practices and design principles must be employed. These practices and principles are centered around monitoring and observability, automation and infrastructure as code, continuous integration and delivery, and management of technical debt. By employing these practices and principles, organizations can develop scalable, reliable, and efficient systems that can efficiently handle variable workloads.